Now I'm going to talk about Lab 3.2. What is the idea behind, what kind of a curve you expect to see inside the lab? The entire idea is this. Generation of a source of energy is expensive. This could be a battery, whatever it is. In an AC domain, this could be the voltage generated by the hydro in Niagara Falls. Then that energy through wires and transmission lines are going to be delivered to the 2 points A and B. For example, if it is AC, then you have Niagara Falls, and this is going to be Toronto, and obviously the transmission lines are going to have some resistivity. If you have a DC, for example, even a cell phone, even the slightest connection between the battery node to the place that is actually utilized is going to present some kind of resistivity and obviously some kind of dissipation, power dissipation. This could be the battery of a computer, and this could be due to the elements involved, the transmission, the lines that are involved, the components that are involved, and eventually delivered to the destination. We want to make sure that the destination is receiving the maximum power. We don't want to waste too much on this side. So we'll see, the question is, what kind of combination do I have, what kind of a choice do I have in order to have the best power delivered to the load? Let's take a look at this and tell me what is happening. Now, if this system is connected, you have a VL, which can be easily calculated through the voltage division principle, and you have an IL. Let's calculate this. VL is equal to, according to the R rule, is RL plus R Thevenin. That's going to be V Thevenin times E, the incoming voltage, V Thevenin. That's my voltage. What is my IL? IL is going to be, you have two resistors in series. It's going to be the summation of both, and then it's going to be V Thevenin divided by R Thevenin plus RL. Let's take a look at the shape of these two variables. Now, when RL is 0, when RL is 0, 0 times IL is going to give me VL0. RL0 is going to result in VL0. Since this is 0, you just put that in and see what happens. IL becomes V Thevenin divided by R Thevenin. We don't do this in the lab, because if you shorten the output, you might actually blow up some of the fuses. So we don't want you to do that. I just want you to see how the system is behaving. Now, if RL is infinity, which is going to resemble the open load, when I say this is open, IL is going to be 0 this time, IL is 0, and therefore VL, you can see it, if IL is 0, this current is 0, the voltage drop across this is 0, and therefore V Thevenin dumps itself across the V open. Now you can see if RL is infinity, that's going to be almost 1 over 1. When you go to the infinity, this ratio is going to be closer to 1. This is 10,000. 10,000 plus 1 is 10,000 divided by 10,001. So in that sense, this is going to be 1 times V Thevenin. So V Thevenin dumps itself onto VL. So this one is going to be V Thevenin. Let's graph this and see how this is going to be. Now, VL. This is RL. This is VL. When RL is 0, I'm going to have 0. When RL is 0, I'm going to have 0. When RL is infinity, I'm going to have maximum available voltage to me, which is V Thevenin. So that's the way it's going to go. This is going to be V Thevenin. Okay? Let's take a look at the current. If this is my current, the curve of current versus RL, see what happens. Now, for RL0, I'm going to have maximum current. Obviously, if you short the output, you expect everything that it can offer to be offered. So this is what is going to be. That's RL as equal to 0, and this is RL as equal to infinity. So you can see that the graph starts from here and eventually dies down to 0. This value is going to be V Thevenin divided by R Thevenin. And this is almost 0. Now, as the resistivity is short, well, what is happening to my power? As this is 0, the voltage is smaller, the current is bigger. As this is bigger, the current is smaller, the voltage is bigger. You can see the shape. That at this time, for example, the power delivered to the load, when this is 0, VL is 0, IL could be anything, the power delivered to the load is 0. When this is open, IL is 0 and VL could be anything, but it doesn't matter because the power delivered to the load would be 0. So I want to have maximum power transfer. Now if I wanted to, and what is my equation? My equation for PL is equal to VL times IL. It's a multiplication of these two. If I wanted to plot this, it would be considering all the units involved. This is PL. 0 times this is going to give me 0. 0 times this is going to give me 0. Obviously, in the middle, it's going to actually reach its maximum. We have shown in the lecture notes that the maximum happens when R Thevenin and RL is the same. We want to verify these graphs, these ones, and we want to see how it works. So we are going to go into the lab, we are going to change RL, we are going to monitor VL and IL. As the RL goes to higher values, the voltage goes up, rises up, the current comes down, and we are going to see that the PL maximum happens when RL is actually the same as R Thevenin. That's the idea of lab 3.2.